Good evening everyone, welcome to 141 Concept Per Day portal. And for the past 2 days I was not able to put the solution for this video. In fact, this question was posted on in my group on I think on last Sunday, and I am giving the solution today anyway. Here afterwards we will try to be regular. Okay, so this question, the first question, which has been taken from 2002 paper, IBDP HL paper. Okay, let us start with this. The question is in two parts. Okay, the first question is the ideal gas behavior. Explain in terms of the microscopic model of an ideal gas and the difference between the temperature of an ideal gas and the internal energy. This is of 4 marks. The expectation is at least 4 points. Okay. The first point is what is the difference between a temperature and the internal energy. That's the first question. So therefore, you can just mention the definition of it. You can say temperature is a measure of the average kinetic energy of molecules in a gas, right? It only takes the average kinetic energy of the molecules in a gas. While what is the internal energy? Internal energy, second point, internal energy is a measure of total energy, okay, which will comprise due to the kinetic energy plus the potential energy, okay. Now this is the second point. Third point, okay, we may ask me, okay, potential energy of a molecule is 0, how is it? But there is also a bond energy, right? So we are considering that part also here. And the third point, so temperature is average kinetic energy per molecule. That's what we can write over here. While the internal energy, 3A and 3B, I can write here. 3A and 3B. I can say internal energy depends on both temperature and number of molecules. What does it tell you? It tells me that whenever the temperature is larger, internal energy also increases. When the number of molecules in the gas increases, even then the internal energy increases. That's what it tells you. And the fourth point, you can say the unit of temperature is Kelvin, while the unit of internal energy what is the unit of internal energy? It is joules. Okay, we have put 4 points. Then second question, an ideal gas is contained in a cylinder fitted with a movable piston. Okay, the mass of the gas is given as so much. This is your mass m, and then the specific heat of the gas is given here. This is C over here. The initial gas is at a temperature of 27 degrees centigrade. Let us say T1. If final temperature is also given, then I can find out T2 minus T1. Okay, that's not given over here. The pressure is given. Okay, that means since I have written T1 here, I'll write T1 also here. Okay, the diagram shows a sketch of the distribution of the molecule speeds of the gas. N is the number of molecules per unit speed interval, and V is the speed. Okay, so everything is given over here. The gas is now heated at a constant volume. Okay, then that means no gas escapes from it. Number of molecules is constant until its pressure becomes 2 into 10 power 5 pascals. See, I have written 1 into 10 power 5 pascals as P1. This should be 2 into 10 power 5 pascals as P2 over here. Sketch on the diagram the molecular speed distribution after the gas has been heated. So this is only a sketch graph. You do not need to add any values. Now what's happening? So you have a piston. Take up the question. You have piston, and in this piston you are keeping the volume constant over here. And what do? You start heating here. You apply Q here. You apply heat energy here. You apply heat energy over here. So as a result of it, the molecules that are present over here will now constantly start pushing it. But unfortunately, you can't change the volume because it says volume is constant. When volume is constant, what will happen? Then the piston will not move outside or inwards, right? Pressure is constant. When pressure is constant, what happens? Then the molecules that are present here will be moving okay, with random velocities. Initially, the molecules would have been moving at lower velocities, but since you heated it, it moves at a much larger velocities, right? Much higher velocities. Therefore, now what should happen to the velocity? The velocity here at initial temperature was here this point. Okay, now what will happen? A more fraction of these molecules. Now the velocity graph will tend like this over here. It will go like this over here and try to go like this over here. It will become a bit asymmetric like this over here. Okay, which means so this goes backwards. This is in accordance with which one? Maxwell's velocity distribution curve. Distribution curve. Okay, what does it tell you? It tells you whenever velocity increases, then the peak number of molecules, most of the number of molecules will have a higher velocity. The peak velocity shifts to the left. Okay, so thus we have got this one here. Okay, and again it depends upon the temperature. Larger the temperature, the more it shifts over here. Okay, so we have drawn this also. Calculate the temperature of the gas and the change in the internal energy. We need to find out what is the temperature of the gas and change in the internal energy. Now let us see what all we have here. Volume is constant. The first thing is volume is constant. When I say volume is constant, then which equation can I use? P1 by T1 is equal to P2 divided by T. Now the question we need to ask is, if all of these are known to you, or any one of them is known, any one of them is unknown, the rest of them are known. Okay. So now let us find out, is P1 known to me? See, P2 is known, P2 is known, T2 is unknown, T2 is unknown. Now if I know P1 and T1, is P1 and T1 known? P1 is known, T1 is known. Let us write down all those values. P1 is 10 power 5, T1 is 27. Okay. So I will write P1 is equal to 10 power 5, T1 is equal to 27 degrees Celsius, P2 is equal to 2 into 10 power 5, and T2 we do not know. Can I just substitute here? I should not substitute. Reason is because this should be kept in Kelvin. So this should now be 273 plus 27, which should be equal to 300 Kelvin, right? So this is a mistake which most of the students do. They just substitute 27 here, get some answer, but that will be incorrect. Okay. So let us get 300 over here. So now let us substitute all of them. So what is P1 10 power 5 divided by 300 is equal to 2 into 10 power 5 divided by T2. Now 10 power 5 goes away. This 2 T2 goes that side. T2 is equal to 2 multiplied by 300, which should be equal to 600 Kelvin. Now we have got the 600 Kelvin temperature we have got. Okay, this was 5 marks number. So we have calculated only one of them. Okay, we'll get 2 marks for this. Change in internal energy. How do you calculate change in internal energy? You have a gas, okay, and then you need to find out what is the change in internal energy. So what is that you have done? You have tried to heat the gas at constant volume. When you heat the gas at constant volume, then the temperature rises, right? So why does the temperature rise? It has a property known as specific heat. What does specific heat do? You provide some energy, and then its work is only to take up that energy and raise its temperature, right? So what is the energy given? The entire energy that you are given, okay, is being converted into internal energy. Why? Because we know that Q is equal to delta Q is equal to delta U plus W. What is this actually? This is your first law of thermodynamics, right? In first law of thermodynamics, what does it tell you? It tells you that whatever heat energy you are supplied, it goes in increasing the internal energy of the substance, plus it also does some work. Now fortunately for us, the work done is equal to 0. Why work done equal to 0? Because it's been performed at constant volume. So what if it is performed at constant volume? Why should work done become 0? Because the expression for work done is given by P times delta V, right? So when I say constant volume, delta V is equal to 0. So W should be equal to 0 here. So therefore, whatever energy you are supplied, it goes in increasing the internal energy of the gas. If I say internal energy of the gas, it only is increasing. That means it raises solely the temperature. Okay. So therefore, if I want to find the internal energy, what is the formula? Delta U should be equal to delta Q. What is the amount of heat energy you have supplied to the gas? So the amount of heat energy supplied is equal to mc delta T, right? So now M, what is M? M is already known to, it was given somewhere over here. Let us look back at the value of M. M value is given by 3.1 into 10 cube. 4 into 10 power minus 3. 4 into 10 power minus 3. I'll write this out. M is equal to 4 into 10 power minus 3 kgs. What's the value of C? 3.1 into 10 to the power of, what is it? 3.1 into 10 power 3. 3.1 into 10 power 3. C equal to 3.1 into 10 to the power of 3. Okay. Now we have got all this value. Now let us substitute it over here. We have Q equal to MC delta T. M is equal to 4 into 10 to the power of minus 3 multiplied by 3.1 into 10 to the power of plus 3 multiplied by delta T. What is delta T? T2 was 600. T1 was, what is T1? 300. So 600 minus 300, which would be 300, which would now be equal to, now let us use our calculator. So this should be 4 multiplied by 3.1 multiplied by 3, which is 37.2 into 10 to the power of, see, I did not use 10 power minus 3, and here also I did not use, these two goes away, plus 3 and minus 3 goes away, and I have double zero here, double zero I'll put like this, which will now be equal to how much? 37 to 3720. 3720. What is this actually? This is the heat energy. This is the amount of heat energy given to the substance to raise its temperature from 300 to 600 Kelvin, and we have also already proved that since volume is constant, the work done is equal to 0, and all the heat energy provided goes only in increasing the internal energy of the substance, according to first law of thermodynamics. Thus, the internal energy is equal to 3720 joules. Now, look at this equations here. 300K, what is this now? One significant figure, one significant figure, 1 SF, everywhere it is only 1 SF except this. Okay, so what you can do is, see, this is, so I can just keep this as 3700 joules also. Okay, now next, the gas is now compressed, put a tilde here, let you find. The gas is now compressed at constant temperature. Now you are going to do it constant temperature. Okay, T equal to constant. The moment anything written as constant temperature, constant volume and so on, what you should have is, you should always say that delta T is equal to 0, delta P equal to 0, delta V equal to 0. It mentions until its volume is half its original volume. That means what? The new volume. Now we have already taken T1, T2, P1, P2. Now volume was constant. What we'll do is we'll take V2 is equal to V1 divided by 2. Okay. What is the change in internal energy of the gas resulting from this compression? Change in internal energy. What will happen? See, when delta T equal to 0, we know that internal energy delta U is directly proportional to change in temperature. When there is no change in temperature, what will happen to delta U? Delta U will also be equal to 0, right? I don't expect any calculations over here because it's already 1 mark. Okay, the moment you see this as 1 mark, you should remember there should not be much of any calculations. Somewhere some logical reasoning should be there. Okay, and that's what we have got here. Okay, next, calculate the pressure of the gas. What is the pressure? Now how do we do? Now what is that we have got? Volume equal to constant. When pressure equal to constant. When pressure equal to constant, V should be proportional to T. Okay, and now how do I find out what is the pressure here? That's the question. Now towards it, which question is this? This is question 2C3. Okay. Now, so when, okay, what is the pressure of the gas? Just a moment. Sorry, this is at constant temperature. I made a mistake here. This is a constant temperature. At constant temperature, what is the equation you can use? You can say P proportional to 1 by V, right? Or P1 V1 is equal to P2 V2. What is P1? Now let us do this one here. Now what is P1? What is P2? We have to look at. What is P1 here? P1 was nothing but the pressure before the volume was changed, right? What was the pressure here? The pressure, where is the pressure here? This was the pressure, 2 into 10 power 5. Okay, so it is 2 into 10 power 5. If you are getting confused with this, what I will do is I will freshly write this one. I will not use this. I'll just erase this because twice you are getting P1, P2, P3 and so on. So this will be confusing. I will just change these notations. Okay, then it will be clear for you. Okay, now here delta T equal to 0. Calculate the pressure of the gas. So you can use delta T equal to 0, which means I can use P2 V2 is equal to P3 V3 because we already use P1 V1, so I'm not going to use this. I'm going to use this one. P2 V2 equal to P3 V3. Now P3 is a new pressure. P2 is a old pressure. Okay, then what is P1? P1 was, okay, I will see here. See here, P1 was the first pressure. Okay, before there was some change in the new pressure. Okay, P1, and then you get P2. Okay, so now you are getting P3 also here. So as a result of this, now P2 is 2 into 10 to the power of 5. And what is V2? V2 is some V2. I will just write V2 itself. I'm not going to calculate, not write anything over here. Why I tell you behind this? This should now be equal to P3. I do not know. P3 I'll write like this. And V3, now if you go back to this here, it says the gas is now compressed at constant temperature until its volume, until its new volume V3 is half of its volume. Half of its volume. Okay. V3 equal to V2 by 2. So what I will do is I'll just write this as V2 divided by 2. So this V2 and this V2 goes away, and you have, this should be equal to P3 by 2. This implies P3 is equal to 2 into 2 into 10 to the power of 5, which should be equal to 4 into 10 to the power of 5 pascals. This should be your answer. Then, during this heating at constant volume, the compression at constant temperature, constant volume and constant temperature, 3500 joules of work is done on the gas. Okay, so work done on the gas is equal to 3500 joules. How much energy does the gas lose to the surroundings during this stage? Okay, why should the gas lose to the surroundings? Now let us understand this clearly. When you heat it at constant volume plus at constant compression, both the time, okay, so when you say you are heating at constant volume, temperature rises. Okay, so here what happens? Temperature rises. We already seen this. Temperature rises. And then compression at constant temperature, which means what? You are slowly compressing this, but while it compresses, okay, you are not giving out any sort of, sorry, the temperature is not going to change. When temperature is not going to change, then you have done so much amount of joules over here. Now the work done here is 0, but there is only work done over here. Okay, see, and so, okay, so when temperature doesn't change, then who will do the compression? Someone should do the compression, right? How will the compression happen? See, when temperature is reduced, then only you can say, okay, there is some amount of compression being done. Okay, so therefore, so if there is no temperature reduction and temperature remains the same, then how will the compression, how will the work be done? So whatever energy you have taken, you have to expand, you have to spend all the energy to the surroundings. So therefore, the energy spent to the surroundings is also equal to whatever is the energy stored in the gas, because temperature is not changing. So this should now be equal to 3500 joules only. Okay, logically we need to write this across. Okay, so with this we come to an end to this problem. So next video we will see the next problem. Thank you.